Okay, excellent. Matt graduated from East Tennessee State University with a master's in applied computer science. His past work has included working on programming models and high performance network libraries. Matt's current work includes monitoring systems at large scale and allowing applications to make decisions at runtime. And I had the pleasure to work with Matt for many years at the Oak National Laboratory. And he's one of the persons who has worked very closely with applications and he's very interested also in from the point of view of programming models and looking at also interesting for programming models for smart NICs. And he's going to give us a talk that is titled Using Data Processing Units to Manage Large Sets of Small Files. And I hope that everybody will enjoy his talk. And Matt, you have the mic.
Thanks, Oscar. So yeah, as Oscar mentioned, I'm Matthew Baker. I work at Oak Ridge National Laboratory. And for most of this talk, I'm going to pick on a particular use case that we had in the past year, which showed a lot of the limits of what we can do currently with our HPC systems, and especially using them for new and novel use cases. So first, I'm going to explain that use case. I'm going to pick on it and explain the deficiencies that we ran into with some of the inefficiencies and some of the early work that we've been doing to address these so that in the future, with smart NIC enabled systems, we can greatly alleviate a lot of these problems and get much better efficiency and throughput and much better utilization of our available compute resources. So the use case in this case is a 1 billion ligand doc, where there is a main database full of small molecules, and we wanted to dock it against a receptor protein. The audience gets 0 points for guessing which protein and why we wanted to dock this so fast. Anyways, so in chemistry, it's a small molecule, but in computer science, it's a text file. It's a text file about 2 to 4 kilobytes in size. Gigabyte would be a decent size. But no, these are fairly small text files, not the sort that just fits in an inode, but also not the sort of thing that's going to map nicely to high performance networking hardware. So ultimately, the goal was to dock 1 billion of these in a day. So we have to be able to get a throughput of around about 20,000 of these text files per second. So the question becomes, how do you actually move this number of small text files? Now, here I've just given an example of part of one of these files. Couldn't put the full thing onto the screen, but it's just a fairly normal text file that you would expect to see anywhere. Some metadata. This remark thing is a comment. And then placing atoms in a 3D space, grouping them together in terms of what can be bent and turned and generally funged around by the docking software. So that's all well and good, but the question becomes, how do we actually manage these? Because as I said, it's usually around 2 kilobytes, but some of the smaller ones, 1 kilobyte, some of the bigger ones, 4 kilobytes, fairly regular. And this is a fairly standard format. Seems like it's one of those things where it was derived from more standard format, and a lot of tools just, settled on this. And these databases are available, and one of the bigger ones contains about 1.3 billion of these files. So not a trivial number of files. But now the question becomes, how do we actually ingest this data in the first place? Well, it comes in much the rest of the software in the Unix universe comes in tarballs. The problem is that these tarballs are in an insane format. And by that, I mean, when you download the smallest possible unit of these files, it's a uncompressed tarball. But that uncompressed tarball contains compressed tarballs. And then those compressed tarballs can contain anywhere from just several hundred files to tens of thousands of files. And there can be many of these tarballs in there where the complete unit is hundreds of thousands of files. And now, from a data processing and data storage standpoint, this sounds terrible. And why would we subject ourselves to this? The answer is because that's what it's provided to you in by the chemists. We didn't have much of a choice on that. So download the files and we get these tarballs that are in formats that we don't particularly like, but how do you address that? You really can't untar all of these into one giant directory. I mean, most of the standard Unix utilities will choke on a couple million files. And so trying to force this into not just a local file system, but a shared network file system, yeah, you're not going to have a good time. Now, in addition to the problem of just storing these files and accessing them, you also need to pre-process these files. Each utility has its own way that it wants you to format and pre-process the files before actually feeding it into the simulation program to do whatever your simulator does with the file. And so the question becomes, where do you do this pre-processing? Now, one idea that seems great on the surface is to just shuttle it to the node. I mean, after all, the CPU tends to be criminally underutilized. On Summit in particular, people don't like using the Power 9 processor because, well, it's Power 9. And the real highlight of the Summit cluster is the accelerators. So you want to pack all these onto the accelerator and have that fed and running its compute cycles. And so, but then there's also the problem that you might want to do this ahead of time, because if you do it before you actually put it onto the node, you can do other things like compress it and store it and make it available for future reuse. So just as an overview of what we're doing here, first and foremost, what we need to do is preserve the original data set. This is tens of thousands of tarballs, and for whatever criticisms we have about the format that we got it in, that is the original. And so that is the base of truth. And whatever computation and simulation happens after that, you must be able to trace it back to the original data source. Then we need to reorganize the data. As mentioned, these tarballs can have anywhere between hundreds and hundreds of thousands of files. And that's not going to work in terms of data distribution, data load, and just the efficient use of our compute resources in general. I mean, these data sources were not meant for our HPC use case. They were meant for the chemists that's able to work the website to down select their data set before downloading. But we don't do small data sets. We do billions of files. And in addition to that, we have to actually pre-process these files. Now, the tool comes with a Python script that will condition the file and produce an output that's suitable for future processing. But you still have to run it over 1.3 billion files somehow. And you want to keep this data because you have to develop the workflow, you have to run it, and then occasionally your program crashes because of course it does. And so being able to keep this pre-processed data so that you don't have to redo the work is of huge value. So this is where we have our workflow. You download 46,000 tarballs from the website of the software vendor that gives your database. And then at Oak Ridge, there is a resource called CADES, which is used for less critical processing, where Summit is where you do your headline work. But if you need to do other tasks, again, pre-processing these files and repackaging them, you can utilize those resources so that you're not burning your much more valuable time. And after that, you get 130,000 tarballs. And then after that, you have your run on Summit, 27,000 nodes. And when you start a job, you're copying a tarball, you set up the program, point it to the source files, tell it to go about docking those files, and then you copy another one to overlap your computation and communication with the storage system. So far, so good. But this model comes with a lot of downsides. In particular, the format is pretty inflexible. Processing all of the tar files ahead of time, talking to application experts, they estimated that about 50,000 ligands per tarball would be optimal. But as we started this Gigadoc, the experience showed that smaller collections of data would have been nice. But we didn't have that knowledge ahead of time. So what we did from the outset, preconditioning this data, was what we were stuck with. In addition, we didn't get to do any data filtering. There was some amount of experience that was gained to show that there was a way to down select some of these molecules for what would not be interesting, but we didn't get to do that. So you have to copy down this tarball, you dock everything in that tarball, and what's in it, well, you'll find out when you unpack it. The next problem is, what's worse than one giant data set? Two giant data sets. So there ended up being two sets of directories where you just couldn't actually use the normal Unix utilities on them. If you did, you would crash your session and you would have to log into a new session, kill the old session, and hope that that actually worked. In addition to that, for all the mistakes that you make ahead of time, you're stuck with them. Since this was a largely manual process and not an automatic process where we could get data processing ahead of time. It took a bit of time to actually get through all the files. Now, once we had this, it was easy enough to run whatever experiments we wanted on this data set, but conditioning the data set in the first place, between all the mistakes and trying to get everything together right, and all the crashes and all the weird things that you get when you have 1.3 billion files, because there's all sorts of exciting things in these files, it took a long time. Now, for this stocking process, it wasn't too painful because we were able to get a small data set to the application developers. They spent their time getting the application up and running. And we ended up with something perfectly reasonable at the end, where these data sets would be copied onto fast local storage, untard. And then we are not even talking about the output here. I mean, you dock the ligand and you want to know how good that docking was and which poses were best. And so your data set's just further exploding here. So the question becomes, how can we make this smarter? How can we have smart storage systems where we alleviate a lot of these problems? Now, the idea that we've been playing with comes down to moving where this processing actually happens. One of the biggest bottlenecks in terms of doing this processing was just shared network file systems. I mean, we did tarballs to get this data set down to a couple 100,000 files, but ew, that's still a lot of files. Not to mention that when doing the reprocessing, you're still having to go through the network file system with all the grossness that's involved with that. So the idea is to use DPUs and SmartNICs to move this compute to some place where it's a lot more profitable. Not only that, but it also has to be easy. The sort of people doing these simulations and dockings aren't computer science experts. Their eyes gloss over when you start talking about IOPS and page caches, and it just needs to be simple. Why can't we just get our data in bulk? Nice and simple. So to this end, one of the best that we've come up with so far is to have a sort of DPU metadata server where you still have the gross file ingest, because there's really no way to solve that. You have to preserve that data in its most native format so that you can trace back all your future work to the original data set. So you have a DPU where after an indexer has run across what you've downloaded, you can then publish what sort of data is available, and then you can send instructions to the storage server on how to repackage, reprocess this data and do it inline. And not only that, but you can store the result on this storage server, and then you only have to, and then if you register this data with UCX, you can publish metadata, which will allow any other compute node to look into what's been done and to extract the useful data. You essentially take like arbitrary real world data and turn it into an object store of processed files, completely bypassing the network file system and all the slowness associated with that. In addition to this, when you push the metadata out to the DPU, you've freed up the storage server resources so that instead of having to worry about keeping track of individual files, you can have it, you can push the compute onto that storage system. It will take up the data, and then all operations are local, and you simply publish the result. And then you just have data processing units talking to each other about how best to process, move, and store these files. Now, one of the nice things about this new work, and especially the DPUs, is that they're essentially general purpose machines. And so you can run high-level programming languages like Python on them. And so we're able to use, especially leverage the UCX Python bindings. This is especially important with the new universe of big data and many files because of the sheer amount of software and the sheer ecosystem available in Python, so that you can spend more time solving your problem rather than reinventing computer science wheels. Now, one thing that I especially want to call attention to is the UCX IO. Now, in Python, they use a concept called duck typing. If it implements quack, it's a duck. Now, in this case, we're doing it with files. So any class that implements seek, read, and write, it's a file. It will just call seek, read, and write happily and not really mind what's going on under the hood. This lets us use the DPU to, instead of pre-processing files ahead of time, we can process them on demand. And so we can collect up files into tarballs, register them with UCX, publish the UCX metadata, and then on the remote node, it can be fooled into thinking that it's just an ordinary, nothing special about it, file handle, even though it's backed by UCX RMA operations. So I have some example code that I have working and have run on some local nodes and some DPUs. This is the client version, where we import the low-level UCX API, perfectly ordinary Python tar file, stand up the UCX context, and here we talk to the remote DPU to ask it what data is available, it has available. From there, we ask it for 5,000 files. Now, this number could be anything you want. So in the previous example where we're talking about the Summit data set, it would start off as 50,000, and then we discover, oh, that's actually not good, and delete a 0. And that's all that changes. And then here we ask the DPU to gather the files together into a UCX memory object. And then our UCX data comes in here. The next slide, I'll show more details on that. But from here, we then start our UCX operations where we create the endpoint that the data pointed us to, unpack an R key to do puts and gets on, feed that into an IO class. And as far as Python's concerned, this UCX IO object, it's a file handle. It doesn't care that it's backed by network operations. Python considers this a file handle, as evidenced by the fact that tar file, which is just a Python standard library file, standard library thing, is able to be given our UCX file handle. and extracts that into the local burst buffer. Now on the DPU, things continue to remain simple in terms of handling all these files. Create an in-memory object, and then given the ligand names that our client asked for, we ask the storage server that the DPU is attached to string the files to us based on the previously run index against the downloaded data. From there, we create our in-memory tarball, and then we map it to a ECX data address that's registered on the DPU for RMA operations. Pack an R key, pack the worker address, and then the ECX metadata gets published. So this will work no matter what your server is running. I have this working on an HTTP server, and I intend to also put it on active message servers. And so you will notice that after the initial read, there's no files. Everything is streaming memory, RMA operations, everything is fast and one-sided. And so I use tar file here just because it's part of the Python standard library. It doesn't have to be a tar file. It can be whatever sort of file storage you want to use. And then it's just shuttling bytes across the network. So where do we go from here? Also, one of the problems is the preconditioner. Do we really want that on the storage server, or can we put that on the local node with its many underutilized processors? Actually, I was actually very interested in the earlier iFunk talk for this. And I think that there's going to be a lot of potential in terms of maximizing our compute center resources in terms of being able to do compute in new places where previously it would have been a huge problem to try and actually set up and orchestrate. And then there's also the question of larger publication of this data. I mean, right now you're directly querying the DPU. Can we do better and higher level? Again, a lot of these users, they don't want to be computer science experts. They want to be able to get their data. And since everything is published over UCX metadata, we're not stuck publishing this on the NIC. The NIC can arrange for the data to be taken elsewhere, processed, published, and then the remote node just needs to know where to look for its data. And then there's also more sophisticated data querying. I mean, nothing here that we've talked about so far allows us to down select data, but this is going to be hugely important as data explodes to be able to take a limited subset of what's available and run over that. And so the ability to query the data directly is going to be critical to this. Anyways, that was my talk on where I see DPUs being used in the future of high performance networking systems and large scale data systems. Anyways, thank you.
Thank you, Matt, for your talk. This was very, very interesting. I just want to check if are there any questions from the audience?
I had one. Thanks for the talk, Matt. I guess I was going to ask, do you do you have like an ideal smart NIC that you think would be really good for this kind of metadata handling? You know, so we're starting to see a few things like FPGA NICs, which granted are really hard to program, CPU-based stuff. You know, we talked about the Inca kind of on-path functionality, and then you have like SP based cores with the Octeon smart NICs. Do you have like a, I guess, do you have a smart NIC that you think would be like your ideal target for extending this?
I would think that a smart NIC that just has gobs and gobs and gobs of memory would be best for this. That you'd have the largest index set possible. That way, you know, each DPU can manage the maximum number of files.
Got it. So yeah, this is like a host server on your NIC now.
Yep, just a bunch of hard drives hanging off of a network card. I mean, that's not entirely fair. I mean, a lot of these preconditioning scripts, you know, I keep wondering how well those would map to other types of compute resources, because right now they just use things like NumPy because everybody loves Python. And so the question becomes, is it possible to do this in a much more like streaming fashion so that as it comes off of the storage server, it goes through some sort of processing element before being packaged up in whatever transfer format you want to use?
Cool. Yeah, that makes sense.
Mm-hmm.
Are there any other questions? Well, I thank you, Matt. This was a great talk. I just want to mention that this problem of ligand and docking has been a big priority at DOE and one of the biggest workloads that we have there, especially as it's a great use case for drug discovery, and especially in these times of COVID-19 therapeutics. And yeah, so some of the work that Matt did was part of a Gordon Bell finalist for COVID-19, and it was very exciting to see a very interesting use case. And I think that there's be a lot of good opportunities to explore basically how to program and how to automate this workflow that he managed to put together, but it can be improved significantly through different levels of APIs and so on. So I encourage to continue these sort of discussions, especially to connect with the different talks and teams in here, so that you know, we can keep exploring this use case and be successful at it in the future. And with that, I will say thank you, Matt. Your talk was really great, and I'm going to be handing over to Pavel Shamis in case he wants to say close down the workshop.